Okay, so the next talk is entitled Optimal Cone Singularities for Conformal Flattening, and it's going to be presented by Yousuf Soliman.
Thanks for the introduction. So the basic problem we're going to be looking at is the following. Given a surface like this bunny, we want to automatically find the best cones that will give us a conformal flattening with the least amount of distortion. So I'll explain in more detail what all of this means, but what we're going to see is that this problem, which really looked like a hard combinatorial optimization problem, reduces to a convex problem where we can easily find the global minimum. Let's take a step back, though, and understand, why do we care about surface flattening? As we've already heard, surface flattening has been used for texture mapping, 3D manufacturing, and machine learning. And in all of these applications, really the quality of the map is extremely important. Ideally, we'd like isometric flattenings, that is with no distortion of lengths or angles. But for general curved surfaces, no such map even exists. Instead, we're going to try and get as close as possible using conformal maps. So a conformal flattening is just one that exactly preserves angles. But even in the best case, these maps can have a lot of area distortion. Large regions of the mesh can be squished into very small regions in the plane. And this really isn't what we want. However, just by adding a few cone singularities, we can almost completely mitigate this distortion. So what exactly are these cones I've been talking about? Well, the basic idea is that you're much better off mapping your surface onto some polyhedron rather than trying to directly flatten it in the plane. For example, consider conformally mapping the globe onto this cube and then cutting it up and laying it out in the plane. Of course, we could have also mapped the globe onto any number of different polyhedra, and the resulting conformal flattenings would each have a different amount of distortion. And this starts to beg the question of which polyhedron is going to give us the least distortion. Before I get to that, though, note that since these polyhedra are completely flat, the choice of cut has no effect on distortion. And in practice, we don't even need to compute the polyhedron. We just need to know where the cone singularities, or vertices, are, and their associated cone angles. And the cone angle is nothing more than the usual angle defect. Now, any surface, no matter how complicated, can be well approximated using cones. And the question that we're going to be looking at is how do we choose the best approximation? Well, an observation from our work is that greedily placing cones according to, let's say, peaks of curvature or conformal scale factors is not a good idea. These optimal cones can end up in seemingly unintuitive places that might even be completely flat. To understand why this is the case, I'll just point out that adding a cone singularity is like approximating your distortion with a harmonic Green's function. These long tails really are significant, and you have this really global optimization problem. What we also see here is that these optimal cones don't just provide marginal improvements over previous work, but rather the real-world payoff is huge. This payoff is especially well pronounced on models like this brain, where it's not at all clear where cones should go. Nevertheless, we find good configurations of cone singularities that provide us with an almost isometric flattening. Now we can play these usual games in the plane, like doing convolutions in a way that starts to look like it would on the curved surface. Now, something which turned out to be quite surprising to us is that we really need to work with measures instead of just functions. Measures are like functions in a lot of ways, but they can also represent these singular features like spikes of curvature at a point or curvature really distributed along a curve. And this might seem like a small technical difference, but it really is the difference between success and failure. For instance, if we naively discretize using functions, we end up with the singularity configurations that are spread out all over the surface. Whereas if we properly discretize using measures, we end up with just a few cones in just the right places. Now, the cones we compute are globally optimal for conformal maps, but by cutting up the surface through these cones, we just have general good surface cuts that are also good for minimizing other parameterization energies. And the reason for this is that once you're already close to being isometric, all maps look more or less the same. And this is really the beauty of working in this conformal setting. It's only here where we can compute globally optimal solutions. Our plan of attack is to first formulate this cone placement problem as a global optimization. It'll be non-convex though, and so we're going to apply an extremely tight convex relaxation, and it'll be framed in terms of measures, so I'll talk about how we can use convex duality or Fenchel-Rockafellar duality as a way to reformulate this in terms of continuous functions. And finally, I'll spend some time talking about how we can discretize and solve this numerically. So to formulate our problem, we need to understand a little bit about conformal maps. Since conformal maps exactly preserve angles, they can be completely described by this real-valued function on the surface called the conformal scale factor. And this just tells us how much stretching or shrinking there is locally. These conformal factors are related to the cone singularities through this linear PDE called the singular Yamabe equation. What it tells us is that the Laplacian of the conformal factors is equal to the curvature of our original surface minus the singular curvature distribution of this cone metric. Now this cone metric is represented by a weighted sum of Dirac delta measures, where the weights in front represent the cone angles. Now we can use this Yamabe equation to write down a nice optimization problem. The idea is we want to find the best configuration of cone points and cone angles that minimizes some total scale distortion, subject to the constraint that the scaling actually describes a cone flattening. And this constraint is nothing more than the singular Yamabe equation. Now we need to understand, how should we quantify distortion? A seemingly natural energy, and one that has shown up in some previous work, is this Dirichlet energy of the conformal factors. But since adding a cone singularity is like adding a harmonic Green's function, this energy is immediately infinite. So we can't use it since it can't even tell us the difference between two different configurations of cones. And if you actually try and minimize this numerically, you end up with extremely unpredictable behavior that depends on the mesh itself rather than the underlying geometry. Instead, we're going to use the simpler L2 norm of the conformal factors. And this has a lot of nice properties, but one is that it's actually this approximation of this nonlinear elastic or ARAP energy. So what you can think about what we're doing is actually minimizing this as rigid as possible energy among all conformal maps. Now the formulation we have is still a bit problematic. The first is that it's in some sense non-convex. As I move a singularity around the surface, the energy will actually fluctuate up and down, making it very difficult to find global minimizers, especially if we're trying to do something like gradient descent. The second issue is that the problem's ill-posed. I can always reduce distortion further and further by adding more and more cone singularities. For example, in the discrete setting, I could simply place a cone at every single vertex and have no distortion whatsoever. Both of these issues can actually be elegantly dealt with using a convex relaxation. The idea is to replace these Dirac deltas with arbitrary curvature distributions and have a sparsity-inducing regularization that pushes us back to being near a cone metric. We're going to have this tuning parameter that's going to essentially give us control over how many singularities we get. And now, this entire optimization problem is actually convex. A tempting way of how to implement this is to use this L1 regularization and just treat this curvature distribution as a function. However, this isn't going to work since minimizers don't even exist in L1. So when we solve this numerically, we end up with, again, behavior that depends on the mesh itself, and we end up with singularities that are spread out all over the surface. And this really isn't the type of singular approximation that we're looking for. Instead, we're going to treat these curvature distributions as measures and replace this L1 norm with this measure space norm. And this is really the natural space to work with since Dirac deltas, which is exactly what we're looking for, live in this space in the smooth setting. And here we see that if treating the seemingly superficial difference properly really gives us optimal configurations of cone singularities. Now the problem is written in terms of measures, so I'll talk about how we can use convex duality really as a means towards discretization. Convex duality just allows us to take an optimization problem over one vector space and provides us with an equivalent optimization problem over its dual. It also gives us these optimality conditions that relate the minimizers of the primal and dual problem, and these are exactly like your KKT conditions or Lagrange multipliers. Now how we're actually going to be able to use convex duality is through this Riesz representation theorem that tells us that the space of measures is actually equal to the dual space of continuous functions. So when we come to this question of how should we discretize measures really in a way that captures a lot of the singular features that we're looking for, the answer at a first glance is more or less, let's not think about it, we'll just use duality. We take our optimization problem written in terms of measures and push it through this framework, and we get an equivalent optimization problem written only in terms of continuous functions, which we know how to properly discretize using piecewise linear finite elements, say. The optimality system that we get out at the end of the day is really quite simple as well. It has a linear PDE constraint, has another linear PDE constraint, and it has this variational inequality, which is something like a box constraint. Now, I want to point out that actually formulating both the optimization and the discretization in a way that exactly satisfies this variational inequality is a key point in actually recovering optimal configurations of cone singularities. So we have this optimality system, and what we're going to do is actually just solve it directly. And this really comes from these well-founded techniques from optimal control called semi-smooth Newton methods, which guarantee that we can actually find solutions and allows us essentially to bake in our discretization of measures. What we're also going to get out is we're going to be able to unambiguously read off both the cone locations and cone angles. And this isn't something that you can do if you try and solve the dual problem directly and then use the optimality condition to recover the cone singularities. So even though everything I've been talking about might seem a little bit complicated, when we actually want to implement this on a mesh, we just need to discretize a few things that we already do all the time. We discretize Gaussian curvature using the usual angle defect. We'll discretize continuous functions using piecewise linear finite elements. And as a result, we get a discretization of the Laplace-Beltrami operator as the usual cotan-Laplace matrix. The algorithm we get out at the end of the day is split up into two stages. In the first stage, we solve a sequence of regularized problems where we get these continuous functions that approximate the optimal cones in a very weak sense. In the second stage, we use these continuous functions essentially as an initialization for recovering the exact cone singularities. The algorithm needs to solve about 20 to 30 linear systems, and it takes about 1 to 2 minutes on a mesh of about 50,000 vertices. In the first stage, at each iteration, we solve these 2V by 2V matrix systems built out of the cotan-Laplace matrix, and the cotan-Laplacian, the mass matrix, and some diagonal matrix. And without going into too many details, I just want to point out again that the exact form of this diagonal matrix really arises from a careful treatment of these measures. In the second stage, we have a 3V by 3V linear system built out of the same basic building blocks. We solve all of these using a standard LU solver. Now we can actually accelerate the algorithm optionally by implementing a simple multi-resolution hierarchy. The idea is to just solve the sequence of regularized problems on coarser meshes and only recover the optimal cones on the finest model. This allows us to only solve about 1 to 2 linear systems on the finest mesh and brings down the runtime to about 10 to 15 seconds on a mesh of about 50,000 vertices. So how does this all work out in practice? What can we actually say about our solutions? Well, what we guarantee is that we find this optimal curvature distribution that minimizes distortion among all other distributions with less total curvature. Essentially what this means is that if I give you our optimal cones, and you give me another configuration of cone singularities with less total cone angle, regardless of whether you have more or less cones, it'll necessarily have more distortion. And this is exactly what we mean by optimal cones. Now, if you recall, we did this convex relaxation. We minimized over things which weren't just Dirac deltas. And so it's natural to ask whether we actually recover cone singularities. Well, what we can show is that given these optimal cones, we can slightly smooth them out in an extremely small distance around the point in a way that slightly brings down distortion. And what this means is that we don't exactly recover cone singularities, but we can get extremely close. Now, of course, we can go the other direction, and using techniques from optimal transport, we can prove that rounding to a nearby cone metric doesn't change the distortion by much. This only shows up in practice on extremely fine models. For example, we needed to refine this hemisphere to have several 100,000 vertices to actually see that the solution wasn't just supported on a single vertex. So here we compare our approach to the method of Ben-Chen et al., which we call CPMS, and this Miles and Zorin approach called GPIF, which is this incremental flattening. And what we find is that our optimal cones provide us with significantly less cones, with much smaller cone angles, and significantly less area distortion. And the reason that we're able to do all of this is, again, we're taking into account the global geometry of the surface really all at once. We also find that our optimal cones just naturally respect the geometry and symmetries of surfaces, whereas these greedy heuristics aren't able to do that. We also have this tuning parameter. If we take it too large, we get no cone singularities. If we take it too small, we get cone singularities everywhere. But in between, we have a lot of control over the number of singularities that we get. This might make you feel a bit uneasy that there is this tuning parameter, but we find the behavior is extremely consistent across a wide variety of models. For example, here we just take lambda equals 0.5 for all of these, and now if you want more or less cones, you can increase or decrease it accordingly. Since we're really minimizing this integral energy and finding globally optimal solutions, we find that our optimal cones are extremely robust to mesh quality, resolution, and noise. As an extreme example, if we add this shot noise where we randomly pull out vertices, we see that these previous approaches, which really are based on pointwise estimates of curvature and conformal scale factors, aren't able to deal with it, whereas our approach completely ignores this. Our framework is also extremely flexible and allows us to jointly optimize over various boundary conditions, and here we use boundary first flattening, which we just heard about. We can also optimize over cones within a fixed range. For example, here we optimize over only positive cone angles. We can also incorporate user-defined notions of optimality. We can incorporate these visibility constraints to only place cones in regions that we can't see, or we can allow the user to paint a preference function on the surface of where they want cones to go. Here we use something like the local feature size. In conclusion, we've really come up with this framework for computing globally optimal configurations of cone singularities for conformal flattening. The algorithm is extremely easy to implement and extremely extensible, allowing the user to have a lot of control over where cones should go. What we see also is that our optimal cones are also really great for other kinds of flattening as well. More importantly, though, what we start to see is that conformal maps are a lot nicer than a lot of us would have expected. By adding just a few cone singularities, we can really reduce distortion. So what's next? Well, one thing that would be nice to incorporate is quantized cone angle constraints. And although this doesn't fit in the current framework, you can sometimes kind of get there by restricting the cone angles to be between plus or minus pi over 2, and occasionally we'll get optimal quantized cones. More broadly, though, we believe that using similar measure-theoretic frameworks can provide new perspectives and efficient algorithms for a wide variety of geometry processing problems like finding optimal surface cuts or optimal singular approximations. The code for this is going to be implemented in the boundary first flattening framework within the coming weeks, and that's all I've got. Thank you.
If anyone has any questions, please go to the microphone.
Thank you, Yousuf. That was very beautiful. I'm wondering if you take a specific mesh and you look at the distribution of cones you get and their angles as you vary the lambda parameter, is there any sense in which the measure you get behaves continuously with respect to lambda, and then how does that affect the actual cones you get?
So I don't actually believe that the cones vary continuously with respect to lambda, although I haven't done too extensive of a study from like a theoretical perspective, but this is kind of what I see in practice. Yeah. And what was the second part of the question? Sorry?
I guess the first part was, does the measure vary continuously? And then the second part was when you sort of round the measure to get discrete cones, do the cones behave continuously? Or like when, I guess, when do the cones split or merge as you change lambda? Or do you just get new cones?
You just get new cones. This is kind of what I've seen from practice, is they don't split continuously, because as you change this lambda parameter, essentially by allowing yourself to have more or less curvature, you end up placing cones in very different regions on the mesh, because it's really kind of this approximation using a sum of harmonic Green's function, so it doesn't really split up continuously, at least from what I've seen. Yeah.
Thank you.
Yeah.
Any other question? So I have a quick question.
Yeah.
When you construct this multi-resolution hierarchy, do you keep lambda the same throughout through the hierarchy, or do you change based on?
Yeah, so lambda's the same. Lambda's this tuning parameter that
Yeah.
we have, and in the sequence of regularized problems, we have a different parameter that just tells us how much smoothing we want to get out of it.
Okay.
But lambda's the same across all of these. Yeah.
Hey, these are extremely impressive results. I just wanted to know, I assume they work for surfaces of any genus, like toruses?
Yeah, so there's an interesting thing that happens once you go into higher genus, where you have a issue with this Gauss-Bonnet constraint, which tells you that this measure norm is always going to be greater than whatever you get from Gauss-Bonnet. And so what you need to do in the case of higher genus is you essentially pop out a disk, or you set one cone at one point to be free. You're allowed to place cones there without penalizing your energy. And just by doing that, you end up with cone singularities on higher genus. But yeah.
Thank you so much.